Welcome back. Today we are going through lesson 11.4, which is about mutually exclusive events. So in today's lesson, we're going to be looking at two different kinds of events. And the first one is when we have overlapping events, and that is where we have one or more possible outcomes in common. So when two events happen, they have something in common, some overlap that's going on. Kind of the opposite of that is those mutually exclusive events. So mutually exclusive events are two events that have no outcomes in common, or they can't happen at the same time. So to look at this a little more, we're going to draw some Venn diagrams here so that we can look at how things go together or don't have any overlap. They're mutually exclusive. So as we go through these events that are happening, we are going to look at what are the possible outcomes and do they have any overlap. So in example A here, it says you randomly select an 8 or a face card from a standard deck of cards. So when we think about a deck of cards, there are 52 total cards that we are looking at. And within those 52 cards, we are trying to see, can we select an 8 and a face card? Can one card that we pick be both an 8 and a face card? So if we think about a standard deck of cards, face cards are like their own numbers, kind of. They come after 10, right? We have Jack, Queen, and King. So there's no card that I can pick that's both an 8 and a face card. So our Venn diagram would have no overlap here. So the two events that are happening are we're selecting an 8 and we're selecting a face card. In a deck of cards, there's 12 total face cards, and there are 4 total 8s, and there's no overlap between those two. All right, so let's look at example B here. In example B, you're randomly selecting a face card or a diamond from a standard deck of cards. So again, still those 52 cards. When we think about this, if I pull out a face card, we're trying to figure out, could that face card also be a diamond? And in this case, yes, it can be. There are face cards. There's a Jack, a Queen, and a King of diamonds. So there's some overlap there. So our Venn diagram for this one would have some overlap. So our possibilities are that we are drawing a face card or we are drawing a diamond card. And then the overlap in the middle here is where both are happening. So I generally like to start my Venn diagrams with that overlap. So when I think about how many face cards are diamonds, we said there's a Jack, Queen, and King of diamonds. So there are 3 that fall into both categories. So when we're thinking about the rest of it, we have to remember that those 3 are already accounted for. The Jack, Queen, and King of diamonds are in there already. So then if we think about the remaining diamonds, well, in a deck of cards, there are 13 total diamond cards, ace through king. 13 total. We've already put 3 of them on there for the face cards, though. So that leaves 10 that are diamonds, but not face cards. If we think about a deck of cards in terms of the face cards, there are 12 face cards total. Jack, King, and Queen of the 4 suits. So 12 total. We've already counted for all the diamonds, though. So that leaves 9 other face cards that aren't diamonds. So that's what my Venn diagram would look like for that one. All right, let's do 2 more down here. So for part C, it says a jar contains 5 blue marbles, numbered 1 to 5, and it contains 4 red marbles that are 1 to 4. You randomly select a red marble or a marble that is odd. So in this case, our 2 events are red and odd. So when we think about our red marbles that are in there, we have 1 to 4. And as we think about that, are there any of those red marbles that are also odd? Well, yes, there is. Odd ones are 1 and 3. So there's some overlap here. So when I draw my Venn diagram, I've got 2 marbles, red 1 and red 3, that are both red and odd. So I've got 2 that fit in both categories. Now, if I think about what's left in the reds, we said there's 4 total. We've already accounted for the 2 odd ones. That leaves 2 that were even. And then the other event that's happening is picking an odd. So remember, we also have these blue marbles going on. And in our blue marbles, we have 1 to 5. So if we're thinking about the odd ones, that would be 1, 3, and 5. So that would be 3 more that are odd but are not red. So that's what my Venn diagram would look like for that situation. I have example D. You're rolling an odd or an even number on a 6-sided die. So when we think about a die, we remember that we have the numbers 1 through 6 on a die. So 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even. So can I roll an odd and an even at the same time? Are there any numbers that are both odd and even in 1 through 6? There are not. So this would be 2 separate things going on. I've got my odds over here. There were 3 of them. And I've got my evens over here. There were also 3 of them. So there is no overlap there. So example 2 is asking us to state whether the events in each of these examples are mutually exclusive or not. So remember, mutually exclusive means they have no overlap. They can't happen at the same time. Not mutually exclusive would mean they do have some overlap. So once we look at the Venn diagrams, these ones are relatively easy to see. So we can see that example A there had no overlap. So we would say those are mutually exclusive, and I'm going to abbreviate here. If we look at example B, we see that there was overlap. You can pick a face and a diamond card at the same time. So we would say those are not mutually exclusive. Example C, the jar with the marbles. There were some marbles that were both red and odd, so those are not mutually exclusive. They can happen at the same time. And then finally we had example D, where we were rolling a dice and we were saying, could an even and an odd number come up at the same time? And in that case, there was no overlap. So those are mutually exclusive events. All right, so we're going to use that idea of mutually exclusive to start to calculate some probabilities now. So when we're finding probabilities with these overlapping events, we sometimes call them compound events, so that's where they can happen at the same time. So for overlapping events, we call that a compound event. It's happening at the same time, or they could both happen at the same time. So the probability formula is there for you. So it says the probability of A happening or B happening. When we have overlapping events, we find the probability of each one individually, but then we have to realize that we've now double counted some events. So if we think back to our examples before where we had, let's say, a face card and a diamond card, if we've counted all the face cards plus all the diamond cards, we've double counted the face cards that are diamonds. So we have to subtract out one probability of those because we've double counted it, basically. If events are mutually exclusive, we don't have to do that. We just have to combine the probability of event A with the probability of event B, because the probability of both of them happening at the same time is 0. It's not going to happen. So we don't need to subtract anything out because there was no overlap happening. So we're going to use those to help us start to calculate some probabilities here. So we're going to go through these 5 examples at the bottom of your page. So the first thing we have to do is we have to decide, are they mutually exclusive or are they not? Do we need to subtract out overlap or do we not? So in this first example A here, it says you roll an odd number or a number greater than 4 on a 6-sided dice. So the first thing we have to think about is it possible to roll an odd number that is also a number greater than 4? And in that case, there is a possibility. So if we think about a dice, we have 1, 2, 3, 4, 5, and 6 on a dice. Odd numbers are 1, 3, and 5. Numbers greater than 4 are 5 and 6. So 5 is some overlap there. So since we have overlapping events going on, we're going to find the probability of each one individually and then subtract out, because these events are not mutually exclusive. So probability of an odd number on a dice. So if we look at our numbers, there are 3 odd numbers out of 6. we're going to add to that the probability of a number greater than 4. So if we look at our numbers greater than 4, there were 2 of them. And then we're going to subtract out the probability of a number that is odd and greater than 4. And we said there was 1 of those. So we're going to subtract out that 1/6. So when we do that, 3 plus 2/6 is 5/6. Subtract out 1/6, we get 4/6. That, again, we can write as a reduced fraction, or we can convert it to a decimal, or we can write that as a percentage. So those are not mutually exclusive events going on. Okay, let's look at B now. A jar contains 8 balls, numbered from 1 to 8. You randomly select a ball that is 1 or 6. So if I pick one ball out of this jar, can I pick a ball that has both 1 and 6 on it? In this case, we can't. They're each numbered with one number only. So I can't pick a 1 and a 6 at the same time. So these would be mutually exclusive events. So in this case, I'm just going to add together the probability of a 1 to the probability of a 6. And that's my overall probability. So there is 1 ball that has a 1 on it out of 8. And there is 1 ball that has a 6 on it out of 8. So together, that makes a probability of 2/8. Reduced, that's 1/4. As a decimal, that's 0.25, which means it's a 25% probability of happening. Okay, let's look at C here. You randomly select an ace or a spade from a standard deck of cards. So thinking about these, is it possible for those to happen at the same time? Can I pull out a card that is both an ace and a spade? And the answer is yes. So these are not mutually exclusive because there is an ace of spades in our deck of cards. So we're going to have to subtract out that overlap. So we're going to say the probability of an ace, if we think about a deck of cards, there are 4 aces out of 52. We're going to add to that the probability of a spade. And if you remember, there are 13 spades in the deck of cards. And then I'm going to subtract out the probability of picking the ace of spades. That one card in there that has both an ace and a spade on it. So there's only one card that's like that I'm going to subtract out because I've double counted it. When I do that, 4 plus 13 is 17, minus the 1, that leaves me 16 out of 52. So that would reduce to 4/13, which is about 0.307 or 30.7% about. Okay, so for our next one, you randomly select a diamond or a club from a standard deck of cards. So thinking about a deck of cards, can I pull one card and it be both a diamond and a club? And in this case, we cannot. So those would be mutually exclusive events, which means I'm going to find the probability of just a diamond. There are 13 diamonds in a deck of cards. And combine that with the probability of finding a club. There are 13 clubs also. And there's no overlap, so we're just going to combine those together. That's 26 out of 52, which is a half, 4.5, or 50%. All right, last but not least here. Out of 200 students in the class, 120 either play sport or are on the honor roll. There are 75 students that play sports and 60 students that are on the honor roll. What's the probability that a randomly selected student is both an athlete and on the honor roll? So looking at it a little bit differently, now kind of some survey results more. So what they're telling us in this problem is that the probability of someone playing a sport, they told us that there are 75 out of the 200 that play sports. Then they tell us the probability of being on the honor roll, which was 60 students out of 200. They also throw in there that 120. So those are students who either play a sport or are on the honor roll. So if we write that one out, that would be 120 students total. So what we don't know is what's the probability of someone playing a sport and being on the honor roll? Because there's got to be some in both categories. So what we're trying to figure out in this case is we know the answer basically, like we've done in the problems before. So we know that there are 120 students out of 200 that are the either or category. What we need to figure out is the probability of the overlap. So we can take what we've done before, where we combine the individual things of happening, which is 75 that play a sport, plus the 60 that are on the honor roll. If we add those together, we're at 135. But the probability of either or happening is only 120. So what I need to figure out is what did I have to subtract in order to get the ones that are both, the overlap, if you will. So we need to figure out what that is. So we said we're at 135 students from the either or categories. That means that to get back to 120 for the separation, then we have 15 too many. So the probability of both is those 15 extras that we have double counted in that problem. So we had 15 out of 200 that were both playing a sport and on the honor roll. If we divide that out, it's about 0.075 or 7.5% of our students that are both. All right, so there's some information on mutually exclusive events. We'll see you next time.